So welcome to my next video. So in this video we will see one more example for the recurrence relation. So just look at this function. This function takes one input n, and inside the function it check whether that n value is greater than 0. If the n value is greater than 0, then it will execute that for loop. The for loop will be executed from the I value equal to 0 to n minus 1. So and inside the for loop it executes only one statement, just printing that I value. So and then once the for loop is completed, the same function is called with the input size n minus 1. So now to form a recurrence relation. So the recurrence relation for this is this function is t of n. So inside this function, this conditional statement is executed for 1 unit time, and this entire for loop. So in the line count method, so we calculate the time taken for a for loop with size n is n. So we can take this as n, and this is the recursive function call with the input size n minus 1. So t of n minus 1. So this t of n is for if n is greater than 0. Suppose if n is equal to 0. Suppose if n equal to 0, so only this if condition will be executed. So for n equal to 0, the t of n value will be 1. So now from this we can form the recursive function. So t of n equal to, so for n is greater than 0, so t of n is equal to 1 plus n plus t of n minus 1. So means t of n minus 1 plus n plus 1. So we can take that n plus 1 as n. So this is if n is greater than 0. And if n equal to 0 means it takes only 1 unit time. So 1 if n equal to 0. So this is the recurrence relation. So now we solve this recurrence relation using substitution method. So to solve this substitution method, just take that t of n value when n is greater than 0. So first we start from that t of n value, and then we reduce the t of n value up to the step k, and once we reach the step k, then we will try to substitute the value of t of n when n equal to 0 in that particular step, and finally we will find the actual value for t of n. So this is the actual method. So this is a substitution method. So just take t of n equal to t of n minus 1 plus n. So take this as step 1. So and then to solve this, to reduce this, we need to know the value for t of n minus 1. So from the t of n value, we can calculate the t of n minus 1 value. So t of n minus 1 equal to, so t of n minus 1 plus n minus 1. So this is equal to t of n minus 2 plus n minus 2. Sorry, n minus 1. So substitute this in this step 1. So now t of n equal to, so t of n minus 2 plus n minus 1 plus n. So this is equal to t of n minus 2 plus n plus n minus 1. So don't add this n plus n minus 1 into 2n minus 1. So finally we need to reduce that d of n value to some known equations or some known value like n log n squared, something like. So If you reduce it, it is very difficult to find the actual sequence. So just we follow the, just we keep that sequence without any change. So keep it as same. Now this, take this as step 2. So this is the step 2. So in order to reduce this step 2, we need the value for t of n minus 2. So from t of n value, the t of n minus 2 can be calculated as t of n minus 2 is nothing but t of n minus 2 minus 1 plus n minus 2. So this is t of n minus 3 plus n minus 2. So substitute this here. So now we can reduce the t of n equal to t of n minus 3 plus n minus 2 plus n plus n minus 1. So this is t of n minus 3 plus n plus n minus 1 plus n minus 2. So in the next step, if you reduce the t of n minus 3, it will give the t of n equal to t of n minus 4 plus n minus 1 plus n minus 2 plus n minus 3. So if we follow the same pattern, we can form the value of t of n at step k. So at step k, so t of n value will be t of n minus k plus n plus n minus 1 plus n minus 2. So plus in between there will be n minus 3, n minus 4, n minus 5 something. So finally it will be n minus k plus n minus k minus 1. Because if it is 3, so at step 3 it is n minus 3 plus n minus 1 plus n minus 2. So in the same way, if it is k, means it will be t of n minus k plus n plus n minus 1 plus n minus 2 plus n minus k minus 2. Sorry, this is actually not n minus k. So it will be n minus k minus 2. So now we only know the value for t of 0. So in order to solve this, we need to change this t of n minus k into t of 0. So how to make n minus k into 0 means n minus k equal to 0. This implies k equal to n. So substitute n wherever there is k. So now t of n. So t of n equal to t of n minus n plus wherever there is k, substitute n. So n plus n minus 1 plus n minus 2 plus, so up to n minus 1. So it will be t of 0 plus n minus 1. So plus n minus 2 So plus it will like n minus 3 plus n minus n plus n sorry minus 1. So this is n minus n 0. So minus 1. So we know t of 0 value is 1 plus n plus n minus 1 plus n minus 2. So up to plus 0 minus 1. So this will be 1 and minus 1 will be cancelled. So n plus n minus 1 plus n minus 2. So plus up to 0. So suppose if n equal to 10. So this will be t of n equal to 10 plus 9 plus 8 plus 7 up to 0. So this is nothing but sum of first 10 numbers. So this is nothing but 10 into 10 plus 1 by 2. So this is actually if n equal to 10. So this is t of 10. So if n equal to 9 means it will be 9 plus 8 plus 7 plus up to plus 0. So this is 9 into 9 plus 1 by 2. So in general, t of n is nothing but n plus n minus 1 plus n minus 2 plus up to 0. So this is n into n plus 1 by 2. So t of n value, finally we reduce the t of n value is n into n plus 1 by 2. So this is somewhat closer to n square. So in big O notation, so now the t of n is closer to n square. So that means the upper bound is here n squared. So we can represent this as big O of n square. So this is actually substitution method. Suppose if you want to solve this by using tree approach. So in the tree approach, we start from t of n. So and then in each step we split that into uh, so two parts. The first part is the time, that is time taken to execute the constant steps, and the next part is the um, recursive function call. So here in each step, so if the input size is n, the constant time it takes is n, and then it calls the next recursive function t of n minus 1. So in t of so in this step, it takes constant type n minus 1, and it will call the next step n minus 2. So here the constant time it will n minus 2, and then it will call t of n minus 3. So it will at one point of time, so that same function will be called with input n equal to 2. So if n equal to 2 means it will, the constant time it takes is 2 unit times, and it calls t of 1. So and then at t of 1, at constant time it takes 1 time unit. So and then it calls t of 0. So in t of 0, the recursive function call will exit. So This is nothing but the constant time that particular function, recursive function calls takes n minus 1, n minus 2. So something here in the 2, 1, and this is 0. So constant time, it will not execute anything. So 0. So in general, this t of n will execute for n time unit. This t of n minus 1 will be executed for n minus 1. This will be executed for n minus 2. So on, it will execute for 2 times. It will execute 1 and it will take 0. So it can. So in total, the total time needed to complete the execution of this recursive function is, so t of n equal to 0 plus 1 plus 2 plus 3 plus, so up to plus n minus 2, so plus n minus 1 plus n. So n minus 1, n minus 2, so 2, 1, 0. So this is nothing but the sum of first n numbers. So this is n into n plus 1 by 2. So this is closer to n square. So we derive the same value for t of n that we derived in the substitution method. So in the tree method also we derive the same value for t of n. So it can be represented in big O notation. It can be represented at big O of n square. So if you are given with any recursive function, first form the recurrence relation for that recursive function. So and then from that recurrence relation, so derive the time complexity using either substitution method or by using tree approach. Thank you.